let's go inside to this like elbow area, this corner of this L-shaped thing, this reverse L shape. And you see, there we go. And that is a star. Welcome back to Arcade. I am Super Tommy, and in this video we're looking at Kaboom.js and A-star pathfinding. Now before we start, if you enjoy our videos, be sure to like and subscribe for more videos on game dev on the web using stuff like Kaboom.js. Now let's get back to what we were doing here with our A-star pathfinding. So A-star pathfinding will let us click on a spot and then have a character find a path to that place to avoid obstacles and give different tiles different costs so that it'll choose the cheapest way to a target destination. So now first thing is we're going to be using the bleeding edge version of Kaboom. So depending on when you watch this video, you may need to install Kaboom via npm install kaboom at next or yarn add kaboom at next. But you may also already, or rather it may already also have, Kaboom may already have the latest version out. So this is the version after sticky type version 0.5. So just check that while you're looking at the tutorial in this video. The syntax may be a little bit different. So with A-star, let's say we have a grid like this, just like this, and there's a coin there that we want to get our character in the bottom right over there to get to. And then the gray parts are just walls that you can't walk through. Now, we want our character to look somewhat intelligent and be able to find their way from where they are to where the coin is while going around the gray walls. Kind of like this, right? That would be the intelligent path. One option is to write it yourself from scratch. Now we've got two videos there to help you do that, to write your own A-star algorithm. And what you'll need to do is first start with breadth first search. And then from there, you can build on top of that to get to A-star. So now we have those two videos in the Arcade YouTube channel. We'll link to it in the description box below. But we're not going to do that in this video. You can check out those two videos. We use Pencil.js to do the rendering, and we go over how to implement the algorithm from scratch. Instead, we're going to use EasyStar, which is a library we can use that implements A-star for us. Now, the only caveat here is that EasyStar represents its world as an array of numbers. And in Kaboom, when you add a level, it's an array of strings. So what we're going to do is to convert the two. So it kind of looks like this, right? In EasyStar, we need the levels to look like that on top. And then in Kaboom, it's that array of strings instead. So we got to do that conversion, and we'll show you how when we code this. So let's go check out how this code is going to look to implement A-star for a top-down game. Okay, so here's our main.ts file. So the first thing we want to do is, of course, to load our tile sheet. So this is the tile sheet we're working with right here. This is from the Faune assets that we use in our character movement video and in our Phaser 3 dungeon crawler tutorial. Well, in that series, we didn't use this tile set, but we used that character set, the character animations from there. But you see, this is the tile set we're using, and just like in the character movement, the 0th index is at the top left, and then we just count 1, 2, 3, 4 all the way across. Then we loop back over to the next row, and we keep going. So that's our tile set that we're going to load. So if we go to main.ts here, this is how we load it with load sprite atlas. This is very similar to, for us when we were loading the Faune character, which we are still doing down here actually, right? So we load our PNG file, then we give it a key to denote what the name of the sprite's going to be, and then some information about it. So now for these tiles over here, we're using tile symbol.grass. This is for Kaboom. So in Kaboom, when we have a blank space, it'll just be a grass tile. That's how we're representing a grass tile. And then we're saying at XY 144.64, at this width and height is where our tile is going to start. So this is basically over 144.64. Let's come here. It's this thing over here. It's, you don't see my mouse, but it's that grass let's see, right there. The point A is not going to quite work, but it's the grass one in the sort of top left area towards the middle, with the daisies over it, and the one below it, that's the grass tile that we're talking about there. So we do it for each one. Grass 2 is the one with those daisies. And so we do it for all the potential tiles that we're going to use, and we got to, define what they are. So this is a bit of a manual process that I've already done, so we don't got to watch me sit here and do it, but you will have to basically figure out where in the tile your tile is, give it a string representation, and then the position that it is inside the tile set, just like that. And let's go to our A-star components. Let me just show you down here. We do the normal loading, then we add our scene, which is the A-star component, and then we just use the go A-star to go to that scene. Now here is the actual scene code. So we have got EasyStar installed with npm install EasyStar.js. We're not using it yet. We're gonna add that code live together. But look here in our level. This is for EasyStar the level array of numbers that we need for EasyStar to tell us how to tell us the path from point A to point B, going around obstacles and choosing the cheapest cost way to a target destination. So we're defining this all here, and let me show you what that actually looks like. Let's go to our preview, and this is what it actually looks like, right? You see here. So it's the green grass, which is most of it. You see in the previous screen with the code, there's grass is most of the actual stuff. And then we've got these plateaus, right? And our character is kind of in the middle there. And we're gonna walk around all this like walls, the like brown ground walls. They're like higher elevated areas that we can't walk through because they're too tall for us. So let's go back to the code there. That's what our definition here is doing. We are basically defining that level. So it's like a lot of stuff here. And we're using an enum so that we can easily change the number that represents the tile if we wanted to. If you go back in here to our tiles, we wanted to switch to a different grass thing. We could easily, without having to go in and manually change every 125 to like 207 or something like that. Now, we have our level for EasyStar, but we want to have the same data give us the same level for both EasyStar and for Kaboom. So what we do here is we actually convert the level. So this is our array of numbers into an array of strings for Kaboom.js. What we do here is we map over the level. So if we have an array of numbers, we map over it. The callback will have a row, which is a array of numbers. And then we do this map inside, which will then convert our number tile number value to a string value for Kaboom. And then we join everything with a empty string so that it's now one string together. So let's look at this tile to symbol. Let's go here. So tile to symbol, simply given a tile value, so this is like 0, 1, 2, 3, 4, it's going to look up what it is the string value should be, and that's where this one is. So we define that over here, so that grass 125 is equal to the empty string that we saw earlier to denote a grass for Kaboom. And basically we just say grass 2 is this value, wall top left is this value, right? So that we can give Kaboom the right thing based on the level defined for EasyStar. All right, let's go back here. Now we're going to talk about these tile space to world space conversion functions in a little bit. Just know that in EasyStar, you're going to get positions in tile coordinates, so not world space. So basically, if you have a world of 50 by 50 tiles, where 0, 0 is the top left and 49, 49 is the bottom right, EasyStar will not give it to you. Will give it to you in basically within those values, like 0, 1, and then like 8, 49, which you then got to convert to your world space. And in your world, each tile is 16 pixels. So at 0, 0, it's really like 16, 16, right? That's how much space it's taking up, not 0 pixels, 0 pixels. So we got to convert that from tile space to world space and from world space to tile space to help us in our math later. There's a lot here. Okay, let's keep going. So here is our start of our component, and we're going to do a simple add level. You've probably seen this before. Normally we would just put the level as a array of strings in here, but we've converted it from our levels array above array of numbers for EasyStar, and then we've converted it to Kaboom. Is the same thing here. Then we define what our tile size is. This is going to be 16. That happens to be the tile size of our tile set. And then, just like we've done before for Kaboom, if you've used this before, each string character that's going to represent something on our map is set here, and then we return a function that returns an array, and in our case this will be used to create our entity. And so we add the components that we want. In this case it's the sprite, so the sprite is going to be tile symbol grass. This is that space, and we've predefined that in main here, right? This is what we're doing here. If you remember, let's go back up here. This is grass space, a empty string space is going to be the grass tile. And so when we use it here, that when it is an empty string space, make this sprite that is the empty grass space. So they just all kind of match. So we did that for every one of the different tile types that we have. So this is a lot, right? I've done all this ahead of time. And here, this is just, I think, a part of Kaboom being a work in progress right now. The typings is not totally accurate. I'm just defining this any function that returns undefined just to get rid of a TypeScript type error. You don't have to worry about that if you're using JavaScript. So now this font character, if you've seen our character movement and animation video, this is all the same thing there. And so now let's get to our actual A-star part. We've talked a lot of stuff, a lot of background information here to set it up so that it can work. Now, what we have is an array here of paths, so of the actual path. And the path is going to be an array of XY positions in tile space. Remember, we're talking about tile space versus world space. This is what EasyStar is going to return back to us, and we're going to store it in this path array. And then with that path array, we're going to, in our determine movement function here, use it to determine where to go, right? So that's how this character is going to automatically move. So we're going to get a path of different tile positions that we need to go through to get to our destination, around different walls and different stuff like that. And then given that information, we're going to use it to know if we should move left, up, right, or down. So let's do code, and it may make a lot more sense than me just trying to explain it. Okay, first thing we need is to make an EasyStar instance. So let's go const EasyStar equals new EasyStar.js. So that's how you make a new instance of EasyStar. Now we want to set the level. So EasyStar dot set level set grid. Give it that level, which you see that it says here grid is an array of numbers. It's an array of numbers, or a matrix of numbers. So that's number array. That's like it's a 2D array of numbers. So that's the level set. Now we're going to tell EasyStar what tiles can be walked on. So EasyStar.set acceptable tiles, and this is going to take either one tile number or an array of tile numbers. So what we're going to do here is say we can walk on tiles.grass, tile.grass, and tile.grass 2. So you can walk on both types of grass tiles only. And now here, so that with A-star, you don't need to do this, but with A-star, you could give different tiles different costs. So for example, if you had water in your world, and let's just say it slows you down, or it's just something that you would prefer any AIs or whatever logic to generally avoid going through water if they can. If there's a better way around than going through water, choose that way. So we can do that by setting different costs for different tiles. It could be mud or ice, whatever. So with EasyStar, we do set tile cost. I think by default the cost is 0 or something like that. So let's just say our second grass tile is slightly more expensive. So let's just say 5. So it'll try to walk around the grass 2 tile if possible, but you can have it as water, ice, mud, hot lava, whatever it may be. So okay, that's the setup for EasyStar. So now when we click on a spot, we want to get EasyStar to return to us a a shortest, cheapest path to that destination. So that's what we're going to do here. And mouse click, this is a Kaboom.js function to let us know where we clicked in the world with our mouse. We're going to pointer back, which is a vec2 with an x and a y, position in world position, right? World position. And we need to give EasyStar things in tile position. So let's look here. This is our character, fane. Let's see, we're going to go from where our character is. So that's fane.position.x and .y. We're going to go world to tile space. Let's look at this real fast. What does this actually do? So what world to tile space does is given some x and y value, we're going to divide by tile size, so that's like 16, and then we're going to floor it so that it rounds down to the nearest integer. So, let's say your number is 386, but divide by 16, you're going to have some sort of fractional number. And then we're going to floor it so they get a whole integer number, and that's going to be the tile index for EasyStar to use. Okay, now same thing here. With our mouse click, it's going to go. It could be anywhere, right? It's not going to land perfectly in a tile position. So we're going to go world to tile to get that mouse click position into tile space. Now, once we have our start position, that's SX, and SY, we're going to go to our target position of TX and TY. So EasyStar.find path. So we want to give it a start X and start Y. So that's SX, SY. And then the end X is TX, TY. So now we have find path. It's going to return a number. And it has a callback, actually. So that's going to be the path. So let's just say, call this points, return. And so we're going to get the points back here. And the points is going to be an array of objects that have an x and y value. And those numbers are in tile space, right? Remember that. So what we want to do here is say path gets points. Just like that, we're setting points into our path. Now for safety, you can always check that this is not null, something like this, so that if for some reason EasyStar can't do anything, you can at least put in an empty array into path. And then to actually make this happen, we're going to call EasyStar.calculate. Now, once we have our path, we need to use it to actually move. So that's what we do here in determine movement. So now if you looked or you watched our character movement and animation video, this would be very similar. We do a very similar thing in determine movement like we did before, but instead of determining what the left, up, and right, down is programmatically, we set these values based on whether your arrow key was pressed or not. Now we're not controlling our character with arrow keys in this example, so we need to basically deduce that based on where our character is and where they're planning to go. So here's how this logic is going to work. We have our path array, an array of x, y in tile space. If there is nothing, we're just going to say return movement, which is this object here, and we're going to just not do any moving. If there's nothing in our path to go to, we're not moving, just say false for everything. But if we do have something in our path array, let's look at the first one, and let's just call this, what's a good name? Target path. The first one, the first element in our list of tile positions to lead us to our destination. Now we have our target tile position. We want to get the x and y. So let's go tx. In this case, it's going to be tile to world because we are in tile space and I get to world space. So target.x, and then let's go ty, tile to world, target.y. So now we have the world space that we need to go to. Now our character fane is in world space, so that's perfect. So now let's check the difference in x and y to know if we should move at all, right? So let's go dx for difference in x and y, and we're going to absolute value this, that if it's in the right spot, depending on whether it's left or right, doesn't matter. If it's not in that right spot, it's going to be greater than 0. So we're going to do math.absolute value. I'm going to do fane.x post.x minus target x, and then dy is similar, but we're going to do y instead, minus ty. So that's dx and dy. So if we've reached our destination down here, this is pre-made code. So if we've reached our destination, that means the difference in x and difference in y is less than or equal to 0, right? So let me do that. So we're going to want this. So if we're already reached our destination, we can get rid of that path, that target destination tile that we're going to. We don't need it anymore. So shift will remove the first element from our path array. So let's imagine our path array has 5 positions, and we've already got to the first one. We don't need to look at it anymore, so we're going to delete it. And then the next time we go through this function, it's going to look at the second one, which is now at index 0. So that's how this works here. Now we could just return. Let's just do that for now. There's going to be a caveat here that we're going to look at right after we implement the basics here. So this is for if you've reached your destination. Now, if you haven't reached your destination, that means that tx and ty is different than Fane's x and y position. So let's actually destructure that x and y. The fane.post. We're going to use it below so that we don't need to keep writing fane.post. Okay, so that's the x and y. So let's come up here. So if fane is, let's say x is less than target x, right? So that means your character is to the left of wherever you want to go. That means you want to go right. So that says right is true. So movement dot right is true. Now else if x is greater than tx. Now if you're to the right of the target, you want to go left. Movement dot left is true. Else if y is less than ty, so you are above, you want to go down. And then of course the only other option here is to go up. So let's see, y is greater than ty. We want to do movement dot up, true. So this, in the way we have it here, you can only move in one direction at a time. You can't go diagonal. This is for simplicity here. Okay, so there's that, and oh, now return, this should be return movement. So we're not going to do any movement if we're already at our destination. Great. Now this action here is this basically the same code as our character movement and animation. So to check out that video to learn what we're doing here, but it's just for moving our character and changing to the right animation. Okay, let's give a preview here and see if this works. All right, so now here's our character in this world. Now if we click on somewhere, it should move, and there it goes. Click here, it moves. You see the animation is a little bit weird. Now we're gonna come back to that shortly. So moving like this works. But now let's pick a place past the character. So I'm going to click over on the left side of the screen. Yeah, you don't see my mouse, but there it is. And you see that it's moving in a path all the way to where my mouse clicked. Now let's pick bottom right here and see how it decides to pick a path. So you see it's going around all the obstacles. It's not running into the wall. It's not doing any of that. And it's going to where it wants to go. Let's go inside to this like elbow area, this corner of this L-shaped thing, this reverse L shape. And you see, there we go. And that is a start. Now you see that the animation itself is a little bit choppy, right? Let me see if I can show it to you. You see, she looks like she's like not really walking. It's more like she's, I don't know, maybe strutting. But that's because there's like an animation error. Let's go back to our code here. There's a error in our logic a little bit. So let's come back up here to this. This is what I was alluding to earlier. Now in this logic, we come through, right? Every frame we're gonna go through this logic here to determine movement. And so we come in on one frame update, and we see that we've reached our destination here, and we're gonna just say, okay, let's toss away that first entry for the position that we're going to next, and then we're just gonna return no movement. So what that of course does is has our character go back to idle, right? 'Cause that's what happens in our action here. If not left or right or up or down, they're all gonna be false. We're gonna end up going to idle. And that's why you see that little like stutter in the walk. So what we can do instead of returning movement, is we're gonna return the function and execute it, determine movement. So we're gonna go through this again recursively, one time really what it's gonna be. And we're gonna come back to the top here, and this theoretically will not be true. Like it should have another path. If not, then it'll just stop and it works fine too. Then we'll go here, and this will be the next target that we were looking to go to, and then we'll go through that same logic, and in the end we'll return which direction our character should go to get to that next position, but we save ourselves from having to stop for one frame first. So let's save that, and I'll show you this is going to be smoother. Okay, so I click over here, you can see that her movement is way smoother. She's actually walking, she's taking full steps. So let me just go all the way across, right? That's a full movement in her animation. It's not this little like pirate leg limp that she has when she's walking. So that's why we had that problem. So you got to return determine movement there so that we don't stop for one frame and then start moving again. So we covered a lot in this video to get HStar working using EasyStar. I don't know about you, but I am tired. And there is a lot that we went through. So hopefully you understood what we did. Just rewatch this video if you need some more help on what's going on. Key parts here is we're going to give EasyStar a level definition that is the array of numbers, defining what tiles can be walked on and what cannot. Tell it to calculate a path for you. It's going to give it to you as an array of tile space values, XY values. Put that into determine movement to determine whether you should move towards that next tile on the path to go to or not. And we'll just move in that direction. Once we get to that tile, we try to find the next one to go to until there's no more positions left in our path array. So if you enjoyed this video, be sure to like and subscribe for more videos on game dev on the web using Kaboom.js and other web technologies. Thanks for watching.